LangChain team, thank you so much for having me. Really excited to share a little bit more about how we made Devin. So my name is Russell Kaplan. I'm president at Cognition. We're the company behind Devin. And as a quick show of hands, how many of you have heard of Devin before? All right, almost everyone. So Devin is an AI software engineer. But we are really focused specifically on working within existing code bases. There's lots of amazing AI tools out there for coding. And what we found is that as the code bases get larger, the problem gets harder. And most of our customers and users around the world are teams. They're teams of engineers or companies full of engineers that are trying to ship real-world products. And so today I want to talk a little bit more about what Devin is, but more importantly, how we built it. And I'm going to share some new sort of technical information we're releasing on exactly how this works under the hood that I'm really excited to present to you all. First, what are we seeing in AI for coding? Obviously, this is a really fast-moving field. And in many ways, software engineering is one of the first large-scale successful applications of generative AI. It started in many ways with Copilots, real-time text completion inside your editor that makes you as an engineer go a bit faster. And now we also have AI IDEs. Again, a development environment for you as an individual engineer to get even more leverage than before, sometimes delegating entire tasks or snippets and really coding in flow with AI assistance. We see Devin as part of a third wave of AI developer tools, which is on the fully autonomous agent end of the spectrum, more AI teammate than AI Copilot. Companies around the world are using Devin like another member of their engineering team, going directly from ticket to pull request, collaborating with Devin in Slack or Jira or Linear. And we see the large majority of Devin sessions and Devin PRs are started from within these other tools, the same way you might interact with another human engineer. Architecturally, this is really different from something that runs locally on your computer. Devin is a cloud AI agent. And what we've seen is that it's very complementary to these local AI development tools. When you are coding yourself and you want to stay in flow and get that speed up, you use a local AI development tool. Where people use Devin is when they're ready to delegate the task entirely. And this is a very different set of technical trade-offs. You get large-scale parallelism, asynchronousness, and the ability to completely delegate individual units of work. In the team setting, this also means that Devins run remotely, not locally. And so they share the same environment across different runs. So you can try many different things in parallel, combine them together. And the teams of engineers who use Devin will break up large-scale engineering outcomes into small individual tasks, delegated to a fleet of Devins, and then coalesce together inside the code base. And the main thing our users look for is for that code from Devin to get merged as pull requests. It also changes the learning model for Devin. In the cloud AI agent setting, Devin is not just for you, it's for your team and for your organization. And so as Devin learns from your interactions, those learnings are not kept only with you. Instead, they're incorporated as part of your team and as part of your organization. And this reliance on organizational knowledge is something that we've seen is really important for working with existing large-scale code bases. Because working with large code bases is really hard. And so I'm going to go into some more detail on exactly how we do this under the hood with Devin. Part one is all about context. If you want to build an AI software engineer, you need to understand existing code. You don't want your AI code contributions to be using a new framework, adding new dependencies, or being done in isolation of what you already have. And code-based understanding is pretty hard. LLMs are amazing at so many things, but they have limited context windows. And even if a code base fits inside the context window, the effective context window is often a lot lower than the advertised context window. We have a series of internal benchmarks that measures effective reasoning capacity across a context, and we find very consistently that the advertised context window is much higher than the effective reasoning context window. Large code bases also have complex dependencies. They can span multiple services, multiple repositories, and they can be intertwined in very complicated ways, even for human engineers. There's huge variations in code quality. there might be some parts of the code base you want Devin to emulate, and some parts you really want Devin to stay away from when it's learning how to be a productive member of your team. Same thing is true for documentation. The code might have comments, might have missing comments, might have documentations that's outright incorrect or misleading. All of these things are part of the technical challenges we work on to make Devin work in real-world code bases. The last critical piece of real-world code bases is that the larger the code base, the more custom it tends to be. Teams and companies build their own proprietary frameworks. They have their own specific jargon. There's context in the code that's not inside the code itself, but the organizational workflow around the code. And so these are the research questions that we set out to solve to make Devin actually useful in the real world. And the first thing I'm going to go into more detail on is something we actually recently released free and publicly for all open source repositories. It's called DeepWiki. DeepWiki is a real-time, continually updated index of your code base published as an interactive wiki, almost like a real-time Confluence page with documentation, diagrams, and the ability to ask questions about your code. We had this originally as an internal data structure for Devin. It wasn't a product. It was just a tool that Devin could use to get high-level context about the code. And what we realized is that human engineers wanted to see this information too. And so we decided to release it as a standalone product and service. So you can take any GitHub URL today and just change the GitHub to deepwiki.com. And for any open source repo, you'll get a full interactive wiki. This also works on your private repos when they're integrated with Devin. And so I looked at the LangChain repo, and we have a full, updated, up-to-date documentation page for LangChain that has not only the pros of how it's organized, the key concepts in LangChain's codebase, but also architectural diagrams and data flows. And we've gotten a lot of feedback from the community that these diagrams are, in some cases, or in many cases, actually better than the diagrams of the official documentation of very popular open source projects, right? Whether it's folks who are on the TypeScript steering committee, the VLLM maintainers, or others, we're getting lots of amazing feedback on how great DeepWiki is. And we've had thousands of code bases start linking to DeepWiki as part of their official documentation. So definitely check this out if you're working on open source code yourself. How does this work under the hood? We just said that LMs are really bad at reasoning about large code bases. I'll give you the high-level algorithm of what we're doing under the hood to generate these wikis. Step one, it's actually not about the code. It's about the concepts. What are the key principles inside this code base that are going to form our table of contents for how we lay out the macro context of this code base? And what we found was that in many cases, those concepts, you don't just get them from the source code itself. There's extremely rich information in the metadata around the source code. For example, was that source code added in as part of a pull request? Well, which member of the team added that pull request? What else have they contributed to? Was there discussion in that pull request about the code? Are there comments? Is there documentation? The git commit history? All of this metadata is a really useful source for building these high context wikis. Once you have those concepts, then you can connect them to the code. So what are the connections between the various code files and the proprietary or specific concepts inside this code base? And after you have that, you need to connect the code itself. There's different sections of the code base. Some files that are more related, less related. There's call traces and flows, and there's a specific way that these different components of the code base connect to each other. You can look at things like the symbol graph, you can look at the call graph, and you can look at how these files tend to be used together. And once you have those code-to-code connections, then you can actually generate a wiki. And for each concept, what we do is we use an agent to go research that concept in the context of the specific code base. We generate a wiki page about it, and then we also provide those intermediate artifacts as context and as tools. And when you put this all together, you get very rich representations of code. And we use graphs as a critical part of those representations. And so this is a graph of the LangChain codebase, where you can see at a high level that different files are more or less related to each other, with a lot of logic in the core, and then maybe outskirts that are more related to test harnesses, documentation, specific integrations with third parties, and so on. And these data structures power a lot of how Devin actually works inside large, million, multi-million line of code bases. So we've got our wiki, but we also need to be able to search the code. And this is another feature that's now mainline in Devin, but started as an internal tool for Devin, the AI software engineer. That's the trend we're seeing, is to make Devin a great software engineer, you need to build tools that are so useful that human engineers want to use them too. And so we have Devin Search, which is essentially deep research on your proprietary code base. Again, whether it's open source or internal. You can ask questions about the code. Devin will scan through that code, try to understand what's going on, using both the micro code, the individual files, but also the macro context it has from this wiki data structure. And it will find this information. For example, I asked, how do I enforce structured output in LangChain? And Devin went and found the right section of the documentation from LangChain, as well as the actual implementation code for what to do. Devin Search gives Devin context. It's an essential part under the hood of how Devin, the autonomous AI agent, can actually make useful changes inside larger team-wide code bases. Once you get a query, you need to do pre-processing. And of course, RAG is a component of that. But we end up doing a lot more under the hood than just RAG, including junk removal, some more advanced filtering of less relevant information and re-ranking, multi-hop search, to end up with this set of context that we think is very, very relevant for this query. And that context, again, includes both source files, but also wiki pages. You need the micro and the macro context to provide really useful recommendations. And from that, we can get a grounded answer. People don't want hallucinations in their wikis, and they don't want hallucinations in their search. So the grounding is essential for this to actually be useful. The second part of how we optimize and customize to existing code bases is a bit more research-oriented. And I'm excited to share a little bit more of some of the post-training and RL that we do under the hood to make Devin work well inside specific narrow domains. We recently released a new model, an open source free model called Kevin, Kernel Devin, Kevin 32B. Kevin outperforms many state-of-the-art foundation models on the narrow domain of writing CUDA kernels. Raise your hand if you've ever heard of a CUDA kernel. All right, we have an audience that's very familiar with the underpinnings of ML. For those who haven't heard of CUDA kernels, this is the source code that you use to write GPU-optimized implementations for NVIDIA GPUs. And so under the hood, when you're using PyTorch or TensorFlow, those high-level graph operations are being executed under the hood by CUDA kernels. And the domain of writing CUDA kernels is extremely rich, because this is a very low-level programming language relative to what many of us operate in more typically day-to-day, say Python. And CUDA kernels were released as Kernel Bench was released as a benchmark by Anne, Simon, Azalea to estimate models' capabilities of generating these very niche, very specific CUDA kernels at high performance and high reliability. And this work from Cognition was done by Carlo, Pietro, Ben, supervised by Silas. These were our research interns who got really, really exciting results from a single project. So let's talk about what this work does more specifically. The goal is to take high-level machine learning code, say a few different calls to PyTorch, and rewrite it as a highly optimized, performant, correct CUDA kernel. This is a very detailed problem domain that many low-level machine learning researchers spend their entire careers optimizing. The design space is quite large for how to write optimal CUDA kernels, and it's quite challenging. What we see in practice in the ML community is that a lot of progress in machine learning is really driven by performance on the hardware. And so even if your algorithm or your new paper is big O optimal, like a linear attention mechanism, under the hood, if your implementation is not efficient, cache-friendly, performant on actual GPU hardware, it tends to not be that useful. So this is a really active research domain for ML researchers. And we want Kevin to be good at writing these optimized CUDA kernels. So how does this work? The first step is to define your reward function. And one of the great things about software, and in particular writing CUDA kernels, is that it's often easy to get automatically verifiable reward. Can you verify the correctness of your code automatically? Well, in this case, we have a less performant reference implementation that we can use to check correctness. And so whenever Kevin, which is our post-train sort of LLM for this project, whenever Kevin writes a kernel, we run it through a series of checks, right? First of all, does that code parse? Is it actually valid CUDA? Does it compile? Does it run? And then after all of that, is it correct? And only if it's correct do we then grade it for performance. How much faster or slower is it than the reference implementation? So with this reward function, notice we don't need a machine learning model here. This is purely a set of automatically verifiable steps, which makes this very, very friendly for high compute RL. Once you have the reward function, you can use it for multi-turn training. And so we use MultiTurn GPO. And for those who aren't familiar, what's going on here is we're taking multiple different trajectories in sequence for this model to get better at writing CUDA code. So on the left here, we have an initial prompt, which results in a chain of thought from the model and an output. And that output may or may not be correct. When we move to the middle of this diagram, we provide eval info back to the model. And this eval info is the results from trying to run that kernel in a real-world GPU environment. There's a lot of work you have to do in terms of sandboxing and isolation to make sure these incorrect CUDA kernels don't mess up your training process or crash your GPUs, and then you're getting accurate performance benchmarks. But we package all that up into almost like a struct of eval information that model can then see as it tries again. And it tries again with a second chain of thought, a second kernel, that gets passed to another step. And this process repeats over several steps. And the result is hopefully a correct kernel. Then you have to distribute your rewards to train this information. And what we found is that you don't want to just reward based on the final output and its correctness or not, and its performance or lack of performance. Actually, the path to get there is also valuable. So you'll notice in red at the bottom here, we have this sum of different rewards discounted by gamma over time. And what that's showing is the very first trajectory, the very first step of that trajectory, gets a reward, even if it wasn't correct itself, if it led to a correct solution and a performance solution downstream. Are you barking up the right tree is basically the reward we want to give the model. And what we found in this project is that being able to do this over multiple iterations with these discounted rewards was really important for this to work, because writing CUDA kernels is hard. And so the reward signal is going to be sparse if you only get one shot. And once you do this, you can find that it's not impossible to very deeply optimize for these narrow problem domains. So in this graph, we have the correctness on the left, how many of the kernels were written correctly by this model. And Kevin 32B is getting 91% correct on this section of the Kernel Bench benchmark that we focused on. And you can see that compared to even 04 mini or 03, this is a significant improvement. This is a narrow domain where high compute RL lets you outperform existing models. On the right, you see performance. So we rewarded Devin proportional to how much speed up Kevin got in this project. And so as the kernels got faster and faster, it got more and more reward. And what we found is that even from a performance standpoint, Kevin 32B is able to outperform these larger scale foundation models. And this was a really interesting result to us because it kind of flies in the face of many sort of broad discussions of, oh, these foundation models are going to be the best at everything, and you should use them exclusively for everything. But what we see internally all the time is that for any given narrow domain, if you can set up your environment to do high compute RL in that domain, it's very feasible to outperform an out-of-the-box foundation model, especially as the open source base models that you start with have improved. To actually make this work in practice, it's important that you keep your model doing what you actually want it to do and not cheating along the way. And this is called reward hacking in RL, and it's in many cases actually challenging to prevent. So I want to show you a few ways that Kevin misbehaved that we had to sort of steer back. So one is Kevin realized that it could write the CUDA and then wrap the whole thing in a try except block and just fall back to the existing PyTorch implementation. And it would always score 100% correct in that case. And it had some chance of being faster than average. But if it wasn't, it sort of defaulted to the 1x. So that was a very unproductive direction for Kevin to go down during the RL process. And we had to make sure that we update the reward function to recognize this type of reward hacking. The second is even a bit more subtle. And so the test harness to make sure that Kevin's code was correct had a class, in this case called model new, that inherited from model. And you can see here what Kevin realized is that it could implement the model as a subclass of nn.module with its attempt at optimized CUDA code. And then it could just overwrite that class name in the namespace. And so you can see it defined a second model new that in this case, just inherits directly from the correct model implementation. So these models got very creative at how to sort of get around your intentions. And this is a challenge in RL. And so making sure you correctly define your environment is really critical to success. And for those of you who have used maybe really popular commercial models, like some of the most popular models for coding, you might have seen that as the models get better, sometimes they're more aggressive at doing things like commenting out your test cases to make sure the work still pass. That's what's going on under the hood. This is a smell of reward hacking. And so it's a constant sort of cat and mouse game between the researchers who are trying to steer these models to do what we actually want and the models that are trying to exploit every possible way to get this high quality reward. So what do we learn from this? Custom post-training can and does outperform frontier models on specific narrow domains. For reinforcement learning specifically, especially in code, it's more compute-bound than data-bound. Kernel Bench, the subset of Kernel Bench that we trained on, only had 180 tasks, which is really not that many when you think about it. But by applying high compute RL, rolling out these trajectories again and again, there is very, very rich reward signal to learn from. And that's because in software, we have an oracle that can help with these rewards. We actually have the environment. We can run the code. We can see if it compiles. We can see how fast it is. And this, in my opinion, is one of the reasons that software and coding specifically has accelerated particularly fast as an AI capability, is that code is one of the few domains where this property holds. I used to lead machine learning at Scale AI, which provides post-training human data for many of the large-scale foundation model labs. And it gets really hard to label by hand high-quality, high-accuracy data as the models get smarter. But code doesn't have that bottleneck because you can continually scale based on automatic signals of correctness. And that's really the third key, is automatic verification allows you to scale. So for your own code bases and your own process, putting in the CI systems, putting in the test coverage, putting in the harnesses that allow that automatic verification is going to future-proof your code as RL and as AI gets better. And we see many of our users of Devin, they first take their code base with Devin and go fix all the test coverage issues. And now that they have full test coverage, it's even faster to use Devin to ship new, more pull requests. The last big point here is I just showed you an example on CUDA kernels. But to me, the more interesting, deeper implication of this research is every code base is in some sense a narrow domain. There are specific things to your code that don't exist in anyone else's code. And that's more and more true the larger your code base is. So you can imagine a future where high compute RL and per code base customization leads to significantly outperforming agents on each individual domain, the equivalent of hiring a software engineer and giving them millions of years of experience working specifically in your environment. So this is some of the research work we've been doing at Cognition that powers Devin under the hood. If you'd like to play around and try this yourself, you can go to devin.ai and sign up for an account, connect it with your existing code, give it a task, and go from ticket to PR. Thank you so much for having me. Thank you.